Okay, we're picking up where we left off in the previous video, going through the opening section on complex numbers. In this video, we're going to talk about performing basic operations with complex numbers. So, how do you add, subtract, multiply, and divide complex numbers? Okay, and now something to point out, though, is that remember that as far as fundamental operations that we learn in algebra, that there's not as many as you think. So you have adding, subtracting, multiplying, dividing. You have powers. You have radicals, so roots, the second root, third root, fourth root, etc. And then after that, all that's left is logarithms and exponentials. Okay, and so we're about to learn how to add, subtract, multiply, and divide complex numbers. And you can think about, once we learn how to multiply complex numbers, then that ties straight into taking any kind of a power of a complex number, okay? But then radicals of complex numbers, so second, third, fourth roots, fifth roots, etc., that we're going to talk about in upcoming sections, okay? And so then all that's left is the idea of logarithms or exponentials, and this textbook doesn't cover that, but that is something that you can learn. How to take the logarithm of a complex number, for example. And I actually do plan to include a video or two on this, talking about the full scope of how complex numbers are used in the algebra playlist. And so I might include that video from the algebra playlist in this playlist as well. Okay. So, but how do you add, subtract, multiply, and divide complex numbers? Well, first of all, just remember, the first thing to remember is that I is a number, just like any other number, just like any other real number. I is just a number. And so you treat it and you operate with it like it's any other number. So, like I squared times I cubed. It's just like the properties of exponents. Is I to the fifth. I minus 3i is minus 2i. Okay? It obeys the exact same properties of every other number. Now, but the way you kind of need to look at I, though, is it is a little bit different from the perspective of, like, if you have I plus 3, there's nothing more you can do with this. You can't simplify this anymore, but if you had two real numbers, 5 plus 3, well, you can combine those. So you kind of treat I like it's a variable. In general, you kind of operate with I like it's an x, okay? So like if you had I times, let's say x plus 3. Well, this would be ix plus 3i. You operate with it like it's a variable. However, the difference, though, is that I has a special definition associated with it, in the sense that x is just x, but you operate with I like it's a variable in a sense, but it's technically not a variable. It doesn't represent some arbitrary number. The meaning of I is that when you square it, you get -1. Or another perspective is the principal root of -1 is equal to I. So it's not actually a variable at all. This doesn't represent some arbitrary number. This is a number that has this meaning. So if in the process of operating with I, if you ever get some exponent of I to where you can break like I to the fifth down into like I squared times I squared, well, then you can simplify that, right? And we're going to talk about simplifying powers of I. So it would make no sense to leave unsimplified some power of I other than just 1. That would make no sense. Because any power of I squared, I cubed, any power of I, you can break it down to be either the I is completely removed or it's just there's a number times I. Okay? Now, as we talked about in the previous video, that there are some nuances that you want to be aware of when dealing with imaginary numbers or complex numbers. Okay? And one of the nuances that we talked about was that, so if you have something like the principal square root of minus 4 times the principal square root of minus 9. Well, we know that based on properties of radicals, that if you have the principal root of c times the principal root of d, you can combine them this way, and that results in the principal root of c times d. But if you performed this property with the principal root of square root of minus 4 times the principal square root of minus 9, and so let's come to the second line here, then you combine them together like that. The minus 1 times minus 1 becomes positive 1, and you get the principal root of 36 is equal to 6. That's incorrect. And the reason why it's incorrect, you can think about, because since you combine those minus 1s, you multiply those minus 1s, you kind of defeated the whole purpose of why we defined I in the first place. So the correct way to do it is, if you've got something like this, then you start by saying, like, you take the I out for both of these. Now you can operate this like you would, anything else in math. So I times I is I squared. You can combine the 9 times 4 like that. So I squared. So I squared is negative 1, so this is minus 6. That's correct. Okay? And really, you can take this attitude. It doesn't just apply to multiplying radicals, like this property of multiplying radicals. You can apply this general attitude to anything any property you're ever using in math. It doesn't matter. So what I mean is that if you're confronted with some problem, and maybe you're going to factor something, so you're going to apply the difference of two cubes formula or something like that. You've got all kind of stuff, and you're going to try and factor it, whatever, anything. Before you start doing math operations, applying math properties, check to see if you've got a term that mixed up in that term is an I value. And then go ahead and simplify it to take out the I value, then proceed forward. Otherwise, you're going to run the risk of kind of circumventing the I. You see? Again, it's not just about this specific radical property. This is illustrating a universal principle you want to apply for any situation, applying any property from algebra, trigonometry, whatever. If you look at your problem and you see, okay, is there a term in this problem that involves an I value? So up to this point, that would just be all we've learned is that you would see a principal square root with a negative under it. But in the future, we're going to learn if you see any even root with a negative under it, then there's an I mixed in with that. So you see one of these radicals that have an I mixed in with it, then don't do anything. Don't start applying properties or simplifying, factoring, whatever. Don't do anything until you take that I out first. Then you can start applying properties and grouping and factoring and multiplying both sides of an equation by this and that, etc. So that's the only nuance in the sense of you can operate with I like it's just any other number. That's the only nuance you want to keep in mind. But multiplying both sides of an equation by, you could do that with complex numbers with I, dividing both sides of an equation by I. You can do anything you want with I. It's just a number. Okay, so now, but we know when it comes to imaginary numbers that they're more generally represented as complex numbers. This right here, the number I, technically, what you have is the complex number 0 plus 1I, with real part 0 and imaginary. It's the complex number with real part 0 and imaginary part 1. And we call this a pure imaginary number. So, okay, how do you add, subtract, multiply, and divide complex numbers? Well, what you can think about is that adding and subtracting and multiplying them is going to be completely straightforward based on everything we just talked about. The fact that the properties of distribution, all of the properties, you just treat I like it's any other number anyway. So what I mean is that, like, for example, how would you add, in general, two complex numbers, A plus BI and C plus DI? So I've got one complex number, A plus BI, and I want to add that to another complex number, c plus di. Well, how would you add these? Well, okay, we treat I like it's kind of like it's a variable, at least as far as how we operate with it. So, okay, well, these two don't contain an I, so that those are like terms, you could say. That's how we add expressions with variables in it. We combine like terms. So, okay, we could say A plus C. Those would combine if we substituted actual numbers for A and B and C and D, those would combine into one number. And then it's kind of like if you had 2x plus 3x, the two, you'd have 2 plus 3 times x. So the 2 and the 3 would combine. So you'd get something like this. And that's it. You started with two complex numbers, you added them, and what you're left with is a new complex number. Yeah, that's it. That's simple. Okay, now what about subtracting two complex numbers? Well, no problem. You put a minus here, but again, like the I is, you just treat it like it's a variable or something. No problem. Because like, again, we're not going to be scared by the fact that, oh, well, what do we do with this minus? Normally we would distribute the minus, but how does that apply for an I? You treat I like it's just any other number. So yeah, just distribute the minus like you would normally do. A plus BI minus C minus DI, and now just combine like terms. So you've got A plus C, and then plus, you would have B minus DI, and there you go. You started with two complex numbers, you're subtracting them, and you get this new complex number here. Okay, and so, that's really simple. But one thing to keep in mind is that the general idea when you're working with complex numbers is that, so you'll start with some math equation, whatever, that has complex numbers, and you can do anything you want with I. You can manipulate the complex numbers, the equation, etc., like it's the expression with I like it's any other number. But once you get to the end and you're trying to like present your final answer, you want to simplify everything, clean it up to present your final answer, you want to come back to the complex number standard form. Like, you don't want to have just I's floating around randomly all over the place. You want to try and group everything to where you can identify complex numbers. Right? Like, we wouldn't want to subtract these two complex numbers and leave it like, so if we did this subtraction, we don't want to leave it like this. You see what I mean? I mean, this is technically not wrong. We haven't done anything wrong starting from this point. But no, you want to, your final answer, you want to go ahead and group everything together to where you can present it as a complex number. So no, you wouldn't want to leave this is correct. You just don't want to leave it like this. Okay, so that's adding and subtracting complex numbers. So now, how would you think about multiplying two complex numbers? Easy. Again, it's just, okay, so we've got one complex number, A plus BI. You've got another complex number, C plus DI. Again, you don't need to be thinking like, oh, well, do the distribution properties still apply here? They absolutely do. There's no issue at all. The only big nuance is, again, if I had mixed in here a even root of a even radical of a negative number, don't start doing the math operations until you've taken the I out. That's the only nuance you need to think about. So, okay, well, just like I would normally do, just treat I like it's a variable. So AC plus ADI plus BCI plus, okay, but what's this last term? BD times I. What do we do there? You treat I like it's a variable. If it was BX times DX, what would that be? That would be BDX squared. So you just do BDI squared. However, as we know, I is not actually a variable. It's helpful to think about it in terms of how you operate with it, in terms of its interaction with real numbers like it's a variable. It's helpful to think about it that way, but it's not actually a variable. I is not a placeholder for, representing just any number. No, I is its own number. Okay, and what does I mean? I means, this is the meaning of I. I squared is -1, or another perspective is this. So again, in a final simplified form, it would make no sense to ever leave I with some power other than 1, ever. If you had I cubed out of the 4th, out of the 5th, you can always simplify that using this fundamental principle here of the meaning of I. And at the end of this video, we're going to talk about simplifying powers of I other than, any power of I. Okay, so this is, you can simplify this because this is, we know I squared is -1. That's the meaning of I. So we're left with okay, so now are we done? Well, no, we haven't done anything wrong. This is correct, but we need to simplify this. And then also keep in mind when you're dealing with imaginary numbers, complex numbers, that at the final answer, you want to put the numbers into their standard complex number form. So, okay, we could combine these two pure real numbers to get this real number over here. And then we could bring these two together. And now we're done, because what we have here, if we actually plugged in values for A, B, C, and D, would be a new complex number. We started with, we're multiplying two separate complex numbers, and what we get is this new complex number. That's it. So that's how you multiply complex numbers. And so now this coincides with, if you wanted to think about like A plus BI to some power, like to the 3rd power, well, we understand the meaning of this. You would just be multiplying this complex number by itself twice. Now, in the upcoming sections, we're going to get a lot more perspective on taking powers of complex numbers. So just stay tuned for that. But I think you can agree the idea of how to do this, if you're willing to go through all the arithmetic, this makes complete sense on how you would actually go about the mechanics of taking a power of a complex number. Okay, now just note though that we're not talking about an exponential of a complex number. Like, we're not saying what is 2 or some base b, some, like an exponential, right? It's a base b that's greater than 0, not equal to 1, some base to a plus bi. We're not that's not what we're talking about here, or like the logarithm of a plus bi. These are more advanced concepts, and I do plan to post a video on these concepts, because again, all we have left to learn is we've just learned how to add, subtract, and multiply complex numbers. We're about to learn how to divide them. In the next section or 2 sections from now, we're going to learn about taking roots of complex numbers. Well, that's it. All that's left is, in terms of the fundamental math operations that we learn in algebra, all that's left is exponentials and logarithms. So that would cover the full scope of operating with complex numbers. So it's pretty cool. Okay. So to find a given product in routine calculations, it is often easier to multiply as with binomials and use the fact that I squared is equal to -1. Yeah, 100%, 100%. You don't need to memorize these formulas here at all. You just treat I like it's any other number. Like it's a variable x, but it's not actually a variable. It's this symbol that has this actual meaning to it. All right, so they work some example problems here of multiplying complex numbers. In the next video, we're gonna work a bunch of examples, but let's take a look at this multiplication. This is a special circumstance here. So if we have 6 plus 5i times 6 minus 5i, and we multiplied this out, why is this a special circumstance? Well, we can see it's a form like this that we remember from algebra. You have like an a plus b times an a minus b. And we know that simplifies to, because like the middle term subtract out, that simplifies to this. All right, so what's the big deal? Well, this is unique when it comes to complex numbers because I squared is -1. So what ends up happening in this case is the I gets eliminated. So with a squared plus b squared, this is going to be 6 squared, or a squared minus b squared, it's going to be 6 squared, and then minus, and then just 5i squared. Okay, so that's 36 minus 25i squared. So it's 36i squared is -1 plus 25. That's 61. And that's a real number. There's no I component. I mean, technically this is a complex number, but there's no, you know, it comes back to just being a real number though. What we think about as just a pure real number. So that's what's unique about this multiplication. And so these two complex numbers here are related in the sense that, if we come up here, that these are conjugates of each other. The term conjugate isn't new. We know the term conjugate from algebra. It's just if you've got two numbers being added or subtracted, the conjugate is just you change the symbol to minus or plus. That's the conjugate. But these are complex conjugates, right? Because it's dealing with complex numbers. So just note, though, don't get confused. If you've got 6 plus 5i, the conjugate of that, the complex conjugate of that is not -6 minus 5i. No, you just change the middle sign and that's it. Now, you always do this when the complex number is in standard form. So no, you don't ever, this is not you don't say the complex conjugate of this is 5i minus 6. No, because you didn't start in the correct standard form of a complex number. No, you start in its standard form, either of these two, and then you flip the sign to addition or subtraction, and that's the complex conjugate. Okay, and what we just saw was that when it comes to complex numbers, that if you have the product of a complex number and its conjugate, then this is going to end up being a real number. There's no imaginary part. Okay, and they give a formula here, and I don't like these formulas because, like, you don't need to memorize any of this because you're going to operate with I and with complex numbers like they're just any other number anyway. Okay, and they say they say a squared plus b squared because when it comes to complex numbers, if we come back here, that you end up getting that you take the I squared out and you end up with a squared plus b squared. Typically, with just real numbers, it's a plus b times a minus b is a squared minus b squared. But because of the I squared that you get, it turns into a squared plus b squared. The coefficient, or the real part, and the real part coefficient, or the imaginary part, you take the sum of the squares of those two. Okay, and so the reason why they're presenting these complex conjugates right now is because we use complex conjugates to divide two complex numbers. So all you do is, okay, let's say we want to divide 3 plus 2i by 5 minus I. Okay, we want to divide one complex number by another complex number. Well, the issue with this is that because in the denominator we don't have a single number, it's not easy to break this up, as we know just dealing with fractions in algebra. Okay, so what we do is we multiply this by 1 in the form of the conjugate of the denominator over the conjugate of the denominator. And so what's going to happen? Well, you're going to get a real number in the denominator. We know that, a single real number. And then in the numerator, you're just multiplying two different complex numbers. That's going to result in another complex number. So if you multiply these two in the numerator and simplify, you're going to get 13 plus 13i, okay? And then if you multiply these conjugates in the denominator, you're going to get 26. Okay, but now we can separate this up into one fraction plus another fraction. And so you can see that you've got 13 over 26 plus 13 over 26i. And that is a brand new complex number. But 13 divided by 26, that's 1/2. So there you go. We started with two complex numbers, one divided by another, and we end with a brand new complex number. So we divided two complex numbers. Okay, now here they do 3 divided by I. So the standard practice would be just multiply. This is 0 plus I, right? So its conjugate would be 0 minus I. Okay, but if you've got a real part that's 0 with a complex number, you technically don't have to multiply even by we could just do this. And that would work fine as well, because we'd get 3i over I squared. So we're done. But but here you get the same answer. Minus I squared is -1, so minus 3i. So yeah, actually, you don't actually have to do the conjugate when it comes to just having a single I in the denominator, an I term. But in general, the idea is you multiply by 1 in the form of the conjugate of the denominator. Because like here, if you did 5 minus 1 in the form of 5 minus I or 5 minus I, that wouldn't work. The whole purpose is to get a single real number in the denominator. That's the whole point. Okay. Complex solutions of quadratic equations, part 2. So let's solve this quadratic equation. This is a little more complicated than what we did in part 1 earlier. Okay, so we bring everything to one side, and then to solve this, we would typically factor, but we can't factor. So we use the quadratic formula, plug everything in, simplify, and get this. Okay, now, again, what's the attitude you're supposed to have when you take a look at something like this? You don't start performing math operations, multiplying by 1 in the form of something, start doing all kind of stuff until you identify, well, look, wait a minute. I've got this, there's an imaginary number mixed up in here. This is an even root, or a square root of a negative number. So I want to stop. Don't do anything. Don't do any math stuff until I account for the I that's involved in this. So you would say 6 plus or minus. We know you take out the I. Okay, now you can proceed forward like this is any other number and do any of the math properties, operations, etc. that you want. No problem. So, okay, the square root of 144 is 12. Okay, now the other kind of thing to keep in mind is that you're not going to make any math errors if you don't do this, but it's good practice to think about that. Once you start, you've taken out the I everywhere, and then you're starting to manipulate the equation, simplify, do properties. But when you get to the end and you're trying to clean everything up and do a final presented form, you want to group the I's into complex numbers. So the standard form of complex numbers. So here we can see we do 6. We can break this up into a real part and an imaginary part. So, okay, 6 divided by 3 is 18. 12 divided by 6 is 2. 18 divided by 6 is 3. So 1/3 plus or minus 2/3 I. And that's the two solutions to this quadratic equation. And you can note, though, that these solutions are what? They're complex conjugates. Just something to note. Okay, now, last topic to talk about in this section is the powers of I. So, again, you could be manipulating an equation. You've taken I's out at different spots, and you could easily end up with powers of I, any kind of power of I. And it would make, again, in the final simplified form, it would make no sense to have any power of I other than 1 in the final simplified form. It would make no sense because you can any other power of I you can simplify. Okay, so what we want to learn here is that if we've got I to the first, well, that's just I, or the second, third, fourth, fifth, sixth, 50th, 60th, I to the 120th. How do you simplify that? Okay, now before we learn that, just note that once we learn how to simplify any positive power of I, then that's going to automatically apply for any negative integer power of I as well. So yeah, we're just talking about integer powers at the moment. But so what I mean is that it's the same idea. If you have I squared, then next is I cubed, then next is I to the 4th. We're multiplying by I, right? Now, but when you go in the other direction, you're dividing by I. So I squared divided by I is just I. Now, what if we keep going? What happens? Divide by I. Well, I divided by I is just 1. So, but the idea is this is I to the 1st, and this is I to the 0. But we divided I to the 1st by I, so we define this to be 1. That's the same way exponents work. Now, if we keep going, divide by I, well, the natural extension of this is I to the minus 1. Because we're going 4, 3, 2, 1, 0, minus 1. Well, we divided 1 by I, so this is 1 over I. So it obeys the same properties. I obeys the same properties as any other number in terms of exponents as well. Okay? And now, again, at the moment, we are just talking about integer powers of I, positive or negative integer powers of I. Non-integer powers we'll have to talk about later. That's a little more advanced. Okay? So, all right, how could you evaluate I to the 50th, I to the 60th? What's a simple way you can approach that? Because obviously the idea is, you could figure it out if you just wrote it all out. We get the concept. I to the 50th, well, okay, just that's a bunch of I squareds, right? Well, we know I squared is -1, so write all this out and then combine the negative ones. So we get the idea. It's not the concept is simple, but what's a systematic way of approaching this to where you don't have to write everything out and take forever figuring it out? Well, okay, what they do is they note that there's a pattern here. So I to the 1st is I squared is -1, okay? I cubed is I squared times I, that's -I. And then I to the 4th is I squared times I squared, so -1 times -1 is 1, okay? Now, I to the 5th is what? I to the 4th times I, so just 1 times I is I. So what you can see is that the pattern is going to start repeating. However, we can take advantage of the fact that I to the 4th is equal to 1. Because if we can take the power of I and break up anything that's divisible by 4 as part of it, then we know that's going to be equal to 1. So okay, so 100 is divisible by 4. So, well, let me give you a simpler example. So I to the 20th, okay? Well, 20 is divisible by 4. That means we can write it as I to the 4th times 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 I to the 4th, right? Well, all of these are equal to 1. So this is equal to 1. So I to any power divisible by 4 is going to be 1. So all we need to do is, if we've got I to the 153 power, okay, all we need to do is take 153, divide it by 4. So 4 times 3 is 12. 8 times 4 is 32. Okay, so we have a remainder of 1. What is that telling us? That's telling us that we can write this as I to the 152 times I. because we know 152 is going to be divisible by 4, because 38 times 4 is going to be 152. Well, this is going to be 1, so we're left with I. And no matter what we do, if we do this process, we're going to end up with I to some power that's divisible by 4 times either I to the first, I squared, or I cubed, which we know is that's easy. I squared is going to be -1, I cubed is going to be -I. So that's the idea of finding integer powers of I.